Sections 20.1 and 20.2. We were working on this day before yesterday. We were working on this day before yesterday. You guys okay with it? Okay. Then we already learned about voltage and we learned about current. Now we're going to learn about resistance and Ohm's law. We'll do some Ohm's law problems. Then we're going to learn about two other things, resistivity and power. Yes, John?
I have no idea where my face is.
Then I will give you another one. I make lots of extras, just for this. Okay. Nick? You guys good?
Another one too.
Oh my gosh.
Oh man, Mason needs one too. Oh, never mind.
Okay. Here we go. We're now looking at resistance. Resistance. Okay. All right. When water goes through a hose, the hose is completely hollow. There's no obstacles in the way of your water flowing through the hose, okay? That's not the way current works. What happens is, if you have a wire, and you've got, let's say, some electron that wants to travel through the wire, he encounters lots and lots of atoms and molecules, and they all have these electron clouds. You see? And so, for this electron to travel through the wire, he cannot just move in a straight line path like water molecules do through a hose. This little electron has to juke and jive. He has to dodge all of these electron clouds so that he can make it through. You guys okay with that idea? And so different materials, different conductors, have more or fewer of these obstacles. So different conductors, it's easier or harder for the electrons to move through them. I think of these electrons as having to run the gauntlet through this wire. Does anyone know what running the gauntlet means? What's that? Is that?
Never mind.
What's that, a fire stick?
No, I was thinking about something else.
Okay. What does it mean to run the gauntlet? Man, I really ran the gauntlet. Does anyone know what that means? Okay, well, I'll tell you what running the gauntlet means. If you ever read a book, my best example of it is, has anyone ever read a book by Ernest Hemingway called For Whom the Bell Tolls? Good for you. You know what it was about, right? Do you remember?
I followed the story of these rebels in the mountains of Spain during the Spanish Civil War.
Oh my God, you even remember? How long ago was it since you read it?
3 or 4 years.
Wow, Gavin, I'd salute you. My goodness, good for you. Hey, that's exactly right. It's about the Spanish Civil War, and it follows these rebels. It follows this one guy in particular. And so you remember this story then, that when these rebels, or I don't even remember if it was the rebels or the other anti-rebels, the pro-government or anti-government, who knows, it's all the same. They have guns and they kill innocent people, you know? And so they take over this town, and when they take over this town, they take the leaders of the town, and they put them here, and then you arrange all of your soldiers in 2 files. Here, just a second. So here's one bunch of soldiers, and here's another bunch of soldiers. Okay? And then you take maybe the mayor of the town or the richest guy in town, and you put him here, and you have him walk in between these 2 rows of rebels. And as he's walking, these guys are kicking them and punching them and hitting them and smacking them with the butt end of their rifles, okay? And so pretty soon they may have started off walking, but in no time at all they're running, okay? And it's called running the gauntlet. because you know you're going as fast as you can because you're being savagely beaten as you go, until finally you get to the end of the gauntlet and you're right there. And now if you're a brave man, if you're a noble man, you just simply walk off the cliff, and then you die. Okay? But if you're not a brave man, if you beg for your life, you fall to your knees and go, please don't kill me, please, please, oh, I don't want to die. Then the head rebel guy shoots you in the head and then kicks you off the cliff and you fall off the cliff anyway. Okay? That's running the gauntlet. So that's what electrons do. When they have to pass through a wire, they got to run the gauntlet. They got to get hit and punched and kicked and spit on, but somehow they make it through. That's called resistance. How much resistance the wire, puts to the flow of charge is called the resistance of the wire. Okay? Well, there's two issues here. One of the issues is current. Okay? How much of this charge is flowing through the wire? And the other concept. Good, no problem. And early eating again. Okay? And the other issue is voltage. Okay? Because voltage is telling me how much energy this charge has. So I'm going to make this positive voltage, and I'm going to pretend that this is positive charge going through here now. But the point is, you have two competing issues. You've got voltage. The more voltage difference there is, the more electromotive force there is, the more current is going to want to flow through this wire. The higher the current will be. But the more resistance the wire has, then the less current there's going to be. And so you get this proportion and inverse proportion thing, where the current is proportional to the voltage, right? The more voltage difference, the more electromotive force, the more current you've got, but current ends up being inversely proportional to the resistance. The more resistance the wire puts up to the flow of current, the less current you're going to have to the flow of charge, the less current you're going to have. And so this culminates in Ohm's law, where current equals voltage over resistance. But more commonly, we like to multiply both sides by R, and so we get V equals IR. And this is actually the more common. Whenever I talk about Ohm's law, I'm always going to say V equals IR. Even though it comes about because current is proportional to the electromotive force, but inversely proportional to the resistance that the wire puts out. You can remember Ohm's law because in Spanish, ir is the irregular verb to go, and the present tense of ir is va, vas, va, vamos, va, all starting with V. Voy, vas, vamos, va. How many people here take Spanish? Well, then you all know what I'm talking about. If you don't take Spanish, you're stuck. But V equals IR, yes?
Wir means man in Latin. V-I-R. That's how you spell wir, and it's man.
Really?
Uh-huh.
Well, there you go.
And you can tell because Chris is in distress right now.
It wasn't a good class.
Wait, what?
Well, we had Latin. When we had Latin for the past 3 years, it hasn't been like an enjoyable experience.
Oh, because that crazy teacher. Yeah, the anti-Mrs. Bryce. Yeah, like the Antichrist, only different. Yeah, I'm sorry to hear that. But now there's no Latin, is there?
There's still Latin.
Well, they do it on Chromebooks, like through Ingenuity or something like that.
Oh, okay, but there's no, you don't have like an adult who knows Latin.
No.
They're using a Spanish teacher.
Oh, really? Who is it? Thomas? I don't even know her. Wow. Okay, well anyway, so there's Ohm's law. So let me give you a situation, alrighty? Suppose I've got a 5-volt battery and it delivers 0.25 amps of current to a resistor, to a resistance. That smells weird. Remember to waft. Always waft. So So we've got this sort of thing, right? This is a 5-volt battery, okay? And it's going through some resistor, okay? And this battery is delivering 0.25 amps. So I want to know how much resistance must that resistor have. I'd like everyone to please do that now. I'll give you a hint. Please use Ohm's law. Okay. How many people are getting 20? Okay, good. 20, right? You're going to get a resistance of 20, and the units are going to be volts per amp. Okay? So we could have kept those units, volts per amp, or we could have converted to the normal SI units. Volts is joules per coulomb, and amps is coulombs per second. So we could have called it 20 joule seconds over coulomb squared. We could have done that. But instead, we want to name the unit of resistance after this guy Ohm, because he made Ohm's law.
Dead white guy.
So because his name starts with an O, Ohm's law, we're going to use the letter O for resistance. But what's the problem with using O? Yeah, it looks a lot like 200, right? So instead, we're going to use a Greek letter for it. We're going to use the Greek letter for O, omicron, okay? And the Greek letter omicron looks like this.
Oh my God.
Now that's not working
Come on
either.
now.
So instead, we're going to use a Greek letter that sounds like O, but doesn't look like O, and that would be omega. So we use capital Omega
There we go.
for resistance. So that's 20 ohms, and it's going to be a capital Omega. Tell me, which letter of the Greek alphabet is omega?
13.
Well, it's not, tell me, you don't have to tell me which particular number. Just think of your Bible, brothers and sisters. Yeah, the last letter, right? Because God is the Alpha and the Omega, according to the Bible, right? So the first and the last. The Alpha is the first letter, Omega is the last letter, right? And when I was at Fuller Seminary, you know, I went to Fuller Seminary for a year before I was a missionary for 2 years in Honduras. And I heard a story how they were building a new church and they were going to have the altar, and above the altar they were going to put Alpha and Omega. And so the builders put Alpha and Omega, except they actually put Alpha and Omicron. So in this church, God was the first and the 2/3 of the way through. Okay, great. So well, let's do another Ohm's Law problem. Here. Please do the example on your sheet. It's example number 2. Please do example number 2 now.
Hey, Mr. Shana, where's Noelle?
Noelle is with Miss Min. Noelle called me. She said, "Can Miss Min make me her slave?" And I said, "Yes." So she is doing things for Miss Min. She's her slave.
Next minute or so studying.
Hmm?
Next minute or so studying.
You should say hi to Noelle.
One right now?
Yeah.
Hi, Noelle. Like I did on calculus.
Yep.
Maybe I should do that every day.
I think she would very much appreciate it.
I think so too, again, because in 20 years, when this is still on YouTube, and Noelle's a 38-year-old housewife, she'll be able to look back on this and go, wow, fun times, fun times.
Gavin's
Okay,
gonna be a
guys.
housewife.
So, so, I have to tell you, as we do more of this, you'll gain way more intuition. Right now, this might feel like just, playing with symbols and numbers, but eventually you'll get a tremendous amount of intuition about this stuff. So here's my light bulb, okay? And it is a 10 ohm light bulb, and it's attached across a 3-volt battery. And so right now, all you're doing is mindlessly plugging in, right? 3 volts equals I times 10 ohms, and so you get 0.3 amps equals current. How many people got 0.3 amps? Yeah, that's it. Let me ask you 2 more questions about this scenario. Here's the first question. What if I cut the wire right there? Would that light bulb still be getting 0.3 amps of current? That is, if a person was standing here with a stopwatch, okay, would that person still be able to count 0.3 coulombs of charge going past every second? How many people say, yeah, sure? How many people say no? Yeah, good for you guys. Sure. Because once you make this cut here, no charge can get past here, which means you just get this big traffic jam, and now nobody's moving, no charge is moving. Let me ask you guys another question. Here, let me connect this up. What if instead of 10 ohms, it was actually 5 ohms? What would the current out of the battery be now? How many people are thinking 0.6 amps? Okay, and the battery will naturally do that. And let me give you an analogy, okay? A battery is a big repository of charge. Just like, if you ever watched America's Funniest Home Videos, have you ever seen those big swimming pools that people have in the backyard where the fat guy jumps in the swimming pool and then the sides all collapse and all the water? You ever seen those? Well, imagine a swimming pool like this, okay? And what all that's happening is, if I have a 10 ohm resistor across this battery, that's equivalent to me putting a little hole right there, and then a bunch of water flows out. And the rate at which water's flowing out depends on how big a hole I cut. If I cut a 10 ohm hole, then I'll get 0.6 amps of water flowing out. If I decide to cut a 5 ohm hole, now I get twice as much water coming out. So it's not like the battery has to think about it. The battery doesn't decide to put out 0.6 amps or 0.3 amps. It's just the nature of the beast, You put 5 ohms of resistance across the battery, then 0.6 amps of current will flow out of the battery in the same way that this water flows out of the pool. Any questions or issues about this? Okay. Then, hey, it's time for you to learn about something else. We are now departing from these notes, and we're on our own now. We're not, there's no notes. I'm gonna do notes on the board, but you're gonna have to dutifully write them down on your paper. It's time to learn about resistivity, a property of metals or conductors. resistivity. We don't usually talk in here, I'll get in the video. We don't usually talk about resistivity of insulators because insulators, you know, no current is going to flow through this insulator. If I put a bunch of charge right here and I have a voltage difference between there and there, this charge isn't going to go that way. It's an insulator. These molecules will just hold on to the charge. Okay? So you can't really have resistivity of an insulator. You can't, your resistor can't be an insulator, you know, because no charge will get past it. Alrighty, so all of this stuff we're talking about, resistance, ohms, these are all conductors, you know? It's just more or less resistance to the flow of charge through the conductor. Alrighty? So let's talk about wires and gauntlets. Suppose I had a wire that was this long, and suppose I had an identical wire, but it was only this long. And I had charge, we'll make it positive charge. Since we in physics land, we tend to talk about current as being the direction of motion of positive charge instead of negative charge. So this charge wants to go down this wire. And let's say it's the same voltage, some positive voltage there, 0 volts there. 0 volts there, some positive volts there. Tell me, which wire is going to put up more resistance to the flow of charge, the long wire or the short wire? More resistance to the flow of charge. That is, think of these as gauntlets for whom the bell tolls. Which is the tougher gauntlet? Which is the gauntlet where it's harder for the charge to get through it? Yes? Yeah. How many people say the longer one? Sure, sure. This is more resistance. Longer wire, more resistance. More resistance to the flow of charge. Okay? But let me give you another wire. How about this wire? It's the same length as that wire, but has a much greater cross-sectional area. Now, which wire has the greater resistance? And I just want to remind you, since V equals IR, I can solve for R, and I get R equals V over I, you know? So more current means less resistance. Less current means more resistance. Which of these two wires has the, let's say, less resistance? Which has less resistance, this wire or that wire? Who's got less resistance? What's that?
The wire one?
This one? Okay. How many people agree with Amani that this has less resistance? That is, that more current is going to flow through this guy. Okay, a few of you. Great, many of you. Imani, why did you say this one?
Well, I was thinking about the example you gave with the beating the guy up. So if they're spread far apart, it'd be harder to beat them up.
Okay, good, good. Someone else tell me, why is Imani's answer correct?
What?
I mean, your answer is good, but there's another reason why. Why is this big fat wire going to have more current in it? Yeah, Sean. Yeah, beautiful. That's exactly right. You know, so for Imani's example, really, they're standing far apart, so many noblemen have to walk the gauntlet. So your chances of getting beat or spit on have been reduced now, because there's lots more people to beat or spit on. Well, I don't know if I can really carry that analogy so further, but I just want to show you this. You know, the analogy I always use is this. Suppose you're in a crowded movie theater and someone yells fire. What do you prefer? Would you prefer the aisles to look like this or the aisles to look like this? Yeah, like this. We're going to get out of the movie theater if we got aisles that look like this. Aisles that look like this, we're stuck. We're all going to burn. You know? Yeah. So I just want you to see that bigger cross-sectional area means less resistance. there's less resistance to the flow of charge when you have a big cross-sectional area because there's a bigger hole for the charge to go through. But there's one more thing resistance depends on besides the length of the wire and the cross-sectional area of the wire, and that's the characteristics of the material itself. Characteristics of the metal, okay? Because you know, some metals conduct electricity better than others. Some metals, their gauntlet isn't nearly as severe as other metals. You guys tell me, what's the best conducting metal that we commonly have access to? Yeah, copper. Good for you guys. You all know that. Copper is the best conductor there is. And it's reasonably cheap. I mean, it's not that cheap, but it's okay cheap. You know, aluminum's cheaper, but aluminum's not nearly as good a conductor as copper. Steel is cheaper, but it's not nearly as good as, well, it's almost as good, but not that good as copper, you know? So yeah, the characteristics of the metal, and the characteristics of the metal we call resistivity. The resistivity of the metal, it's given by the Greek letter rho. And so these are the three things that the resistance of a wire or any conductor depend on: length, cross-sectional area, and resistivity. And so we get this equation. Resistance equals rho times L over A. The resistance of wire is the resistivity times the length over the cross-sectional area, where L equals length and A equals cross-sectional area. Alrighty. Hey, let's do a problem. Here it comes. Find the resistance of a 2-meter long copper, and it turns out that the resistivity of copper is equal to 1.72 times 10 to the negative 8th ohm meters. Wire of cross-sectional area. What cross-sectional area did I use on this one? 5? 5 times 10 to the negative 7th square meters. Good luck. I just want you to mindlessly plug into that stupid formula. Thank you very much. Alrighty. Resistance equals 1.72. And hopefully you see that the units work out to just ohms. And what'd you guys get? What'd you get, Robbie?
0.069.
Good enough, 0.069. Do you mind if I just round to 0.07?
Yes.
Yeah, 0.07 ohms, which is a very, very small resistance, as you'll find out later in this class. But that's for 2 meters of wire. What if I'm running wire from Hoover Dam to Rancho Cucamonga, which is 200 miles? Well, now the resistance of the wire starts to become significant, you know? But 2 meters of wire, no, very little resistance. Any questions or issue on this? Then hey, let me give you another problem. Suppose I had a wire. Here's my wire. It has a particular length, L, and it's got a particular cross-sectional area, A, and its resistance is 20 ohms. And then I decide to melt that wire down and double the length. So now this wire is twice as long. Of course, it's going to have to get thinner because it's the same volume. I melted this wire down. It's got twice the length. And now I want to know what the new resistance of this wire is. That new resistance, is it 10 ohms, 20 ohms, 40 ohms, or 80 ohms? Please think about this and we'll have a vote. Last period, only one person got it right, and that was Raghav. Why does he laugh? Did I say his name wrong or something?
No.
He's the only one.
Resistance equals
This is
to
the, I
the length.
want Video Land. Raghav Wadhawan? Wadhawan? But anyway, that was just him. He was it. He was the only guy. Let's see if anyone gets it right in here. Maybe it'll be nobody. You guys laugh at him now, but when you get it wrong, you won't be laughing. Or maybe you will.
The length. Type in.
Yes.
Does the area stay the same?
You tell me. The volume stays the same.
Well,
I know that for sure because I'm melting this wire down and reforming it. Who's the Greek? Is it a Greek god or a Roman god who forges metal?
Both.
Is that?
Both Greek and Roman. Greek is Hephaestus, Roman
Vulcan.
is Vulcan, yeah.
Vulcan. Okay, Vulcan. Yeah. Vulcan.
well, you had a bigger cross section.
So you know that Vulcan?
Decrease
Good for you.
cross-section.
I didn't, but I
So
remember.
you increase.
Okay, great. You guys ready to vote?
Yeah.
Here we go. How many people say 10 ohms? 1, 2. Okay. How many people say 20 ohms? 1, 2, 3, 4, 5, 6, 7 of you. Okay. How many people say 40 ohms? 1, 2, 3, 4, 5, 6, 7 of you. Okay. And how many people say 80 ohms? 1, 2, 3, 4, 5. Okay, 5 of you. Great. First of all, someone explain to the class, how is it there's no chance it could be 10? Yeah.
There's a longer wire. Longer wires have more resistance.
Yeah, it's a longer wire, so it's going to have more resistance. And what did I do to the cross-sectional area?
It's smaller.
I made it smaller because it's the same wire, so that makes it have even less, or rather even more resistance, right? Because where's the formula? You know, yeah. I mean, I increased L and I decreased A, so both have the effect of raising resistance. So we know it can't possibly be this. Also, since I raised L and lowered A, it can't be that. It can't stay the same. So it's really between 40 and 80. Someone who chose 80. Why 80? DeAndre.
Because not only are you increasing the length, but you're decreasing the cross-sectional area by 1/2.
Good. Great. Because remember, volume is equal to cross-sectional area times length, right? So if I cut the length in half, I'm sorry, I didn't cut the length in half, I doubled it. So if I double the length, I had to cut the cross-sectional area in half to maintain the same volume. So you guys okay that it's 80 ohms? Just like DeAndre said. I doubled the length and I cut the cross-sectional area in half. It's 80. Any question or problem on that? Good. Well, I got 5 people in this class who got it right. That's good. That's better. That's progress. Yeah. Okay, great. Hey, that's it for resistivity. It is now time to learn about power, and then we'll be done. And power is pretty easy. This is all pretty easy. You're going to love chapter 20. Except when we hit Kirchhoff's laws. That may not be so easy. All right. Am I going to run out of memory on my video?
Nope, you're fine.
Yay, thank you.
You have over 100 minutes.
Oh, sweet. Now I can just talk and talk and talk for 100 minutes. Nice. Okay, great. Power. I just want to remind you, power is energy per unit time, energy over time, and it's also work over time. And I want to remind you the units are joules per second, but we call those watts. Okay? Power starts to become important when we have processes that last a long time. You know, it's not very useful to talk about the energy the lights use because the light's going to be on for varying amounts of time and usually really long amounts of time. And so with lights being on, we talk about the power, how many joules they use per second. Then we just multiply by the number of seconds. That's how much energy it uses. We found that to be true also sound. Do you remember, and I'm just going to put parenthetically, do you remember sound intensity? Where it had the units of watts per square meter? And again, because sounds tend to be long lasting, sounds tend to last, you know, the length of a song or the length of whatever. So we end up, it's just more useful to talk about the watts of the, you know, the power the sound is putting out rather than the energy. But anyway, we're going to go ahead and get the power of our situation. Do you remember yesterday or 2 days ago, we talked about this, where electrical potential energy per unit charge, how that was equal to voltage, volts. Okay? And so I can divide both sides, I can multiply both sides by Q, and I get my electrical potential energy, which, by the way, also ends up being the work, depending on whether that electrical potential energy is lost in doing work. And that ends up being a Q times volts, right? And then the next thing I'm going to do is this. I'm just going to divide both sides of this equation by time. So now, whether it's work per unit time or electrical potential per unit time, it ends up being power. And Q over delta V, you tell me, what's Q over, or sorry, delta T. What's Q over delta T? What's coulombs per second? What do we call that?
Charge.
What's that? Yeah, charge. Charge per unit time, though. What special name do we give charge per unit time? When the guy with the stopwatch is watching the charge go by, what do we call that? Yeah, it's current, right? Current. So this is going to be current times voltage, and there it is. Power is current times voltage. It tells you how much power your circuit is dissipating. And I can't say it any easier than that. P equals IV. So hey, let's say I've got a battery, and it's up to a light bulb, okay? And suppose this is a 12-volt battery, and this battery is putting out 1/2 amp of current. How much power is that light bulb dissipating? What'd you guys get? Yeah, 6 watts. Good for you. 0.5 amps. times 12 volts. Yeah, 6 watts. Okay, let me ask you another question. Since this is a 12-volt battery and it's putting out 0.5 amps, what must be the resistance of that light bulb? How many ohms resistance must that light bulb have if you put a 12-volt battery across it and the battery puts out 0.5 amps? How many ohms? What's the resistance of this battery, of this light bulb? I'll give you a hint. V equals IR. Use Ohm's law. First one to shout out the answer wins. Yes, Fatima.
24.
How many people agree with Fatima? 24. 0. One of you. Yeah, you got to get, you're going to buy in 2 weeks, you will be so fast on something like this, you'll be like immediate, you know? Because I'm going, okay, V equals IR. I got a 12-volt battery. I got 0.5 amps. What's the resistance? Hey, 24 ohms, right? 24 ohms. So I want you to see, you can use V equals IR and you can use power equals IV in conjunction. Let me give you another problem. Are you ready?
Yes.
I am now going to get rid of this light bulb and put in a new light bulb, okay, whose resistance is only 12 ohms. I'd like you to find me the current, and I'd like you to find me the power. I've got this new 12 ohm light bulb that I've put in the place of the 24 ohm light bulb. What's the current? What's the power? You do that now. To get the current, you're going to have to use V equals IR, Ohm's law. To get the power, you're going to have to use power equals IV. Okay, time's up. Who got the current? 12 ohms, 12 volts. What's the current? How many people got 1 amp? Yay. So I got 1 amp. So tell me, how much power is this light bulb dissipating now? Yeah, hopefully you're going IV. And so this is going to be 1 amp times 12 volts. And hey, that's 12 watts. Okay? So yeah, do you see, by putting in a light bulb with less resistance, I've got a light bulb that dissipates more power. I've got a light bulb that's brighter, okay? And that's the way that works. The last thing I need to tell you, and you've been listening to me for the entire period, and I really appreciate it. Here comes the last thing. We have 2 other equations for power by inserting Ohm's law. Okay? Remember how power is equal to IV? Well, I can substitute IR for V. That's Ohm's law. So I get a new formula for power, I squared R. Or, because Ohm's law says V equals IR, which means V over R equals I can substitute V over R for I, and I get V squared over R. So which of those 3 you use just depends on what they give you. If you get a problem where they give you voltage and resistance, then go ahead and use that guy. If you get a problem where they give you current and resistance, use that guy. But if they give you current and voltage, use that guy. It's that simple. Hey, any questions or issues on anything you've learned today? I should get in the frame there. You guys okay? All right, then bye-bye. Toodaloo.